All right, this video is going to talk a little bit about what we call exponential decay functions. Now, you should have already learned about exponential growth functions. You may remember functions that look like the one on the left here, or if you were looking at an application problem, right, y plus some initial amount times 1 plus r, 1 plus r. Again, the guaranteeing that this number is greater than 1. So down here right below, let's say we're multiplying again times 1.25, and again, raised to the x, or over and over and over again. Your growth factor, again, is 1.25 because our growth rate, right, the R value was just 0.25. We're growing. So notice if we graph that out, you're going to get that green function right there, right? The one with the green points. 1.025 to the 0 would have been 1, and 1 times 2 was 2. So we started right there on the y-axis at 2. But then from then on, we just got larger and larger and larger, right, numbers. So it's not like a linear function where we get a straight line. We get this curve that increases. Well, when we talk about exponential decay functions, notice the major difference in our formula. 1 minus r this time. 1 minus r. So this time, again, if our decay rate is 0.25, right, we're losing a quarter of what we had every time. Not gaining, but losing a quarter. Again, we're going to say 1 minus 0.25 then, which gave us 0.75. We're losing a quarter of what we had. We're gaining, or we're keeping, you could say, not really gaining, but keeping 0.75, 75%. Right? So notice up here we've got 16. So we're going to start off at 16 up top here, right? But 16 times 0.75 once is 12. Right? 12 times 0.75 drops down to this point here, right? Going to be at about, what is that? 9.5 or 8.5, 9 actually, right? 0.75 times 12 would be 9. And notice we're going down, 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 down. But notice, again, we're still multiplying by a positive value. So no matter what, our number is going to stay positive, right? Positive number times a positive number, we're going to stay above 0 every single time, right? We're getting smaller and smaller and smaller and smaller, getting closer and closer to 0, but we're still going to have, we've talked about it before, what we call that horizontal asymptote, right? ASYP MP TOTE. Horizontal asymptote at y equals 0. Our range, all of our y values, right, our range of y values are all still greater than 0. They're still above 0. So kind of keep that in mind. We're decaying, but we're never going to completely disappear. And in that case, that's why when we apply exponential decay functions, okay, we have a couple of good examples here. Car depreciation. Technically, your car can lose value, but it'll always be worth something to somebody, right? So a car depreciation value, when you buy a car and you drive it off the lot, it loses some of its value. No, it's a used car, right? Medical dosages do the same thing. Again, you put a medical dosage in your body, right? They give you a shot, right? A flu shot or something like that. Or you, let's say, take some aspirin, right, over here. Well, initially, there's a lot of aspirin in your system. But after a little while, your body sort of, cleans your body out, right? It cleans it out and it cleans it out some more. But kind of the funny part is, at some point, it approaches 0, but technically the percentage of the amount should always stay above 0. There's always an infinitesimally tiny amount. Now, in the real world, yeah, your body may have completely cleaned that out. But again, to model that, we use exponential decay. And it really helps for half-life of elements. So like if you have a carbon-14 or even like uranium or plutonium, right, those scary radioactive decay kind of things, they're scary because they have what's called a half-life. After a certain amount of time, half of that element will always be there. So it works great for carbon dating, things like bones, right, over here, like this nice skull here, right? Because half of the amount, right, even if it's a 10 grams, now it becomes 5 grams, 5 becomes 2.5, even if it's 0.002 grams, right? Well, now there's still 0.001 grams. Half of that will be left. after large amounts of time much of the time. Carbon-14 takes a long time. It's great for dating things like dinosaur bones, right? After thousands of years, there's still some left. And because we know how much is left, we can figure out how much started, right? If we know how much is left very far in the future, we can go backwards and figure out, well, how much was there when we first started? So we can figure out how old things are. Again, the major idea, 1 minus r is going to be our decay function. Decay factor is 1 minus r. Same as b in our old y equals ab to the x. If b is less than 1, right? If b is less than 1, then every time we multiply by that fraction, right, times a half, times a half, times a half, every time we multiply, we're going to get a smaller and smaller number. Your decay rate, right, your decay rate, just r, is still a percentage, though, right? It's still a certain amount that's going to disappear. Let's see what that looks like. So if you buy a 2015 Ford Edge, and you bought it for $28,000, right, $28,700, the value of the car will be less each year because of what we call depreciation. Think of that like decay, right? The value of your car is decaying away. The car loses value at a rate of 12% each year. So let's write a decay model. So the amount that it's worth is going to be equal to the initial amount, $28,700, times 1 minus what we're losing. And now remember, 12%, I need to move that decimal 2 spots. That's 0.12, right? So I'm going to say 0.12 for r there, right? 1 minus r. And again, we're going to write that model for any number of years, so let's call it t up here, right? But again, this is your r value. This was your c, or your principal value, right? Your initial amount. And again, t is going to be our number of years. Okay, number of years. What will the value of your car be after 5 years? Well, again, the value of the car will be equal to 28,700 times. Now notice 1 minus 0.12, we can actually go find that number. 1 minus 0.12 is 0.88, or basically saying we're losing 12% of our value, but we're keeping 88%, right? It's still worth 88%. We're just losing a small amount. We're losing 12%. And again, we're going to 5 years, so we're going to say raised to the 5th. So I'm going to type that in my calculator real quick here, 28,700 times 0.88 raised to the 5, and we'll find out that our car after 5 years is now worth a measly $15,000, right? $15,145.91, rounded accurately there. We bought it for almost $30,000, and it's less than, almost less than half of that now, right? Almost less than half of that after just a short 5 years. Now, don't be depressed about that. That's not a big deal. Almost anything you buy in life usually goes down in value, right? It becomes a used thing. That's why we buy it, though. We buy them to use them. But just realize that that's a good example right there as far as the money you're going to lose on various amounts. Let's talk about that medical idea. Again, let's say they gave us a equation here this time, y equals c times 0.7 to the t. What if we wanted to find the amount of medication in a person's bloodstream after 3 hours? Now notice this time the concentration y, right? After taking c milligrams, right? Our initial amount is going to be in milligrams, and in t hours. This time our time is in hours. So how much, right? After taking 1,000 milligrams will be left? 0.7 raised to the t. Again, the amount of time was just 3 hours. So we took 1,000 milligrams to start with, and 3 short hours later, right? 3 short hours later, we only have 343 milligrams still remaining. Right? So, kind of makes sense, right? But remember, we still have some left, right? There is still some left. Let's say we just kind of change the question a little bit. I'm just going to throw this in here. What if we took 1,000 times 0.7? But let's say it was, how about a couple of days later? How about we say 100 hours later, right? More than 3 days later. In fact, more than 4 days later. Well, 1,000 times 0.7 raised to the 100th is technically still 3.23 times 10 to the negative 13th. Now, it's not much. 10 to the negative 13th is a really small number, right? But there's still some there. So looking at the model, by what percent does the medication decrease in the bloodstream every hour? Or essentially, what's your decay rate? Well, remember, 0.7 is our decay factor, right? It's 1 minus R. So if I subtracted a 1 here on both sides, I get negative 0.3. And then if I divide by negative 1, what I'll quickly find out is, again, 70% of it, right? 0.7 was sticking around, but 0.3, right, was our R value. 30%, right, of our value, right? 0.3, so 1, 2, 30% of it is still sticking around, or so it was disappearing. 70% stays, 30% goes. If you have any questions about applying exponential decay, make sure you talk to your teacher. Otherwise, have a great day.